Hello again and welcome back. My name is Michael Fudge. This is lesson 15 in learning to program in Java. In this lesson, we'll take a look at searching and sorting collections of data. On today's agenda, we'll look at what are sorting and searching. We'll talk about built-in sorting and searching algorithms that are built into the Java class library versus rolling your own. And of course, supply you with a wide variety of code demos. Before we begin, let's explore the concepts of sorting and searching. While these concepts seem rather trivial, I still like to discuss them in detail. So sorting is the act of arranging a collection in an order. So for example, before I have a collection of integers 6, 7, 2, 5, 3, and then I've rearranged that collection in numerical order from lowest to highest, 2, 3, 5, 6, 7. So when you sort, you're rearranging a set of data. Searching involves finding a specific value in a collection. For example, I have the same collection before, 6, 7, 2, 5, 3, and if I try to find the 5, it returns the position 3, 0, 1, 2, 3. So that 5 is at position 3. If I try to find an 8, because the 8 does not exist in the collection, it returns a non-existent value from the collection, like a negative value. As you can imagine, sorting and searching are quite common when you're programming with collections, especially when you're solving problems that use business data, that is, data that you're going to present to the user. When we think about how we use any kind of business data, usually we want to organize it in a certain way. You might want to sort that data by last name or first name or phone number. You might want to try to find a particular person. You might want to find them by their name or by their ID number or maybe by their email address. So searching and sorting are very common practices in programming, especially when you're dealing with collections of user-oriented business data. One important thing to remember is that we as programmers are inherently lazy, and this is a good thing. And by lazy, what I mean is efficient. That's the big joke. And what I really mean by efficient is that we don't like to reinvent the wheel. You should never write code that already exists and that you know works well. For example, in the Java Util Collections package, there are algorithms that do sorting and searching for us. And why write our own sorting and searching algorithms when these exist? If they exist and they suit our needs, we should use them. So that's kind of going to be a big story today, is that while I will show you custom sorting and searching algorithms, it's mainstream practice for me to not write my own algorithms, but to use the ones that already exist in the Java class libraries. You should do the same thing. So in Java Util Collections, we're going to look at two methods. One is called collections.sort, which you can use to sort an array list. And the other is called collections.binarySearch, which you can use to find a value in an array list. The interesting thing about doing a binary search is it's really fast, but it needs a precondition. You cannot use a binary search on data that hasn't been sorted already. So a common pattern when we go to search for data is we first sort it, then we search for it using the binary search method. You can certainly write your own search method if you don't want to use a binary search method that works on unsorted data, and I will show you that in the example. Before I can sort or use binary search in the Java Util Collections library, I first need to create a class that implements something called a comparator. And a comparator is a very special class which returns an integer comparison of two objects. So if you take two objects and compare them, and object A is less than B, the comparator should return a negative value. When A equals B, the comparator should return a 0. And when A is bigger than B, the comparator should return a positive number. If you do that, you have implemented a comparator properly, and then the collections.sort and collections.binarySearch methods will know exactly how to sort your data. Again, I'll do an example and it'll make a heck of a lot more sense. Okay, enough with the talk. It's time to get down and do some action. The first example, we'll use some basic sorting and searching algorithms, some that I've rolled myself, others that we grabbed out of Java Util Collections. In the second example, we'll look at how you can apply this to objects, collections of objects, right? When you have an object like a student, what does it mean to sort a student? Are you sorting them by their name or by their GPA? What we'll do is we'll write a custom comparator that will deal with how we want to sort the student, and then apply that to the Java util collection sort method to get it to sort in the right order. Okay, here I am in my NetBeans IDE, and I have created a class called Basic Sorting and Searching Demo. And this example starts out with some code that I already wrote. This code is not very exciting, but let me just show you what it does. It generates 20 random numbers, adds them to an array list, and then prints them out unsorted. So for example, if you look up here, I am creating my array list in line 13. Then I have a for loop in line 14 that goes from 0 to 19, so that's 20 times through the loop. Each time I'm adding what I generate from the random number generator as a next integer between 100 and 1. So I'm adding that to my collection. Then I'm printing out the word unsorted, as I did down here. Then I am calling the print numbers method, which if we look at that, it just goes through all the collection. So it starts at 0 and goes up to nums.size. And for each item in the collection, it prints it out, nums.getI. So I get the ith member of the collection and print it. And then that prints out my numbers. Also what I wrote was I wrote two of my own algorithms. Down here I wrote what's called a linear search, and if you Google linear search, you'll find all sorts of information on the internet about how to do it. What a linear search does is it starts at one end of a list of numbers. I'm going to point down here. So it would start at 88, and then it just keeps going through the list until it finds the value it's looking for. I've called that value target. As soon as it finds target, it sets the variable found to the index, that is the position in the collection, and then breaks out of the for loop, and then because it found it, it doesn't need to keep going. In the event that it goes all the way through this collection and doesn't find the value I'm looking for, what it will do is just return a -1, which means it wasn't found, the position wasn't found. So what I'd like to do first is let's implement a find method and then print out a message based on whether or not we found a value. So I already have a variable called found up here. I'm going to use it in my main method. I'm going to call find. I'm going to pass in my numbers, which is my collection that I want to find the value in. And let's suppose I want to find a 50. Now this is going to return a number. If that number is 0 through numbers.size, then what we have here is we found that 50 in the collection. If it's a -1, then we didn't find the value in the collection. So I'm going to create a print statement like this. You don't want to watch me type it, which will do the following. It's going to say the number and then 50 was string found, and the string is either going to say nothing or not, depending on if found is less than 0, it's going to say not. Otherwise, it's not going to say anything, which says it was found. Let's give it a run and see what happens. So the first time through, I get my unsorted list, and it says 50 was found. Let's see if we can locate the 50 in my collection. There it is. So let's run it again and see if we can get 50 not found. 50 was not found, and if you look through this collection, you will not see a 50 in there. All right, easy enough. Okay, next what I want to do is I want to sort my collection of numbers and then once again search for the value using the binary search method. And rather than sort them using my custom sort algorithm that I used down here, I did a bubble sort. I am going to use the collections.sort method. So I'm going to say collections.sort. And if I bring up the Java docs on sort, you'll see that it takes two arguments. It takes the list of things you want to sort plus a comparator. So as I said before, and if you want to use collections.sort or collections.binary search, you have to provide your own object of class comparator. What I want to do now is I'm going to pass in my collection. And then in here I need to say new object of type comparator, which I have not written yet. So I need to write that first. Let's do that now. New Java class. I'm going to call this integer comparator. Now, first thing first, I need to make this integer comparator implement a common interface. So I need to say implements a comparator of integers. You always need this when you write a custom comparator, is you need to say this thing I'm making called an integer comparator will implement a common interface of comparators for integers. If I was going to make a comparator for students, I would say comparator and then students would go in here instead of integers. It needs to know what it's comparing. Now my comparator needs one method, and it's always the same. It's called compare, and it returns an int, as we said before. If it returns a negative value, then that means that the thing I'm comparing to is less than the other thing. So in this case, when a is less than b, I want a negative value. When a is equal to b, I want 0. And when a is greater than b, I want a positive value. One other thing when you implement this method is you have to use the override annotation. This means that you're replacing an existing method with this compare method. And what I want to do at this point is return a minus b. And that's going to be good enough. Now let's just think about what this is doing for a minute, because this seems like incredibly trivial code, but most elegant code is trivial code. What this says is when I compare a and b, if they're the same, then when I subtract them, there should be 0. If a is bigger than b, then if I subtract them, it should be a positive value. If a is less than b and I subtract them, it should be a negative value. So this is a very simple implementation of compare for my integer comparator. You'll see later on when we write comparators for the students class, it gets a little more complicated than that, because we have to decide what it means for two values to be the same or different. But with integers, it just makes logical sense to do this. So again, I want to just reiterate what we did here was we made our own class, and this class is our version of what it means to compare integers. That's what this is saying over here. Okay, and then we defined what that means, and we override it because we're replacing the default behavior of what it means to compare integers. Now this is what it always means to compare integers, but I wanted to show you what a custom comparator looks like. Now we can go over here in numbers and use our comparator. We make a new object of class integer comparator. And that's it. This line will now sort those numbers. How does it know how to sort them? It uses the code in here to compare any two values, figures out which ones are less than the other, and then rearranges them. If I wanted to sort them so that the highest numbers are first, I'd have to write a different comparator for that. And maybe if there's time at the end of the lesson, I'll do that. Okay, now what I want to print is the numbers again, and maybe the word sorted. So let's do this. Let's say now they're sorted, because I called sort. And then let's reprint them. So let's see what we get now. Let's run it. Unsorted. Sorted. Ta-da! Just to show you something really quick, right? If I wanted to make a comparator that sorted them in the other order, I really should make another class to do that. But all I can do is if I swap A and B, it should sort them in the other order. Watch this. Ta-da! And if you just think about what we did here, you'll understand why it does that, right? Because now what you're saying is when B is bigger than A, right, it's positive. So now it's going to compare them in the opposite direction, which is why it sorts differently. I also could have written this as negative A minus B. Could have done that instead. Same thing. If you're an algebra buff, you'll know why. But I'll just leave it as that. That's what I want. Yes, and it's still sorting in ascending order. Okay, let's finish it off. Now that we have a sorted collection, we can use the binary search method, which is much more efficient at finding numbers than a linear search. And the way we use binary search is very similar to what we did in the linear search. We just call collections.binarysearch instead. And of course, we need a comparator, so we're going to say found gets, you see it takes a list, a key, and a comparator. So I'm going to give it a list, which is numbers, a key, which I want to find the 50 in there, and then the comparator I'm going to use is I'm going to make another object of type integer comparator. Now, do I have to do this new? I could have up here, said comparator C gets new integer comparator, and then just put C in here. But I'm okay with doing this. That will search for it, and then my same code up here can help me determine if I found it and print it out. Okay, so I'm going to find it with binary search using my comparator, and then this same print is the same as this print. It'll just tell me if I found it. Of course, if I found it up here, I'm going to find it down here. It's the same collection. So 50 was found. Let's see, 50 is right there. Now I've rearranged the collection, and 50 is right here, but it's still found. See how that works? Let's run it again and see if we can get 50 not found. Okay, 50 was not found here, and of course, even if I sort it, it's still not found. So hopefully that explains how to do some sorting and searching of collections. Again, sorting is the rearrangement of your data in the collection, and searching is finding a specific value in that collection. And it doesn't make sense to write your own sorting and searching algorithms down here like I did. I wrote this one here sort, this one here find. It doesn't make sense to do that when you can just use the ones available to you in Java util collections. Collections sort, collections binary search. The caveat of binary search, though, is you cannot use binary search until you first sort the collection. So if you want to search it without sorting, you're going to have to write your own linear search. This next example is like the previous example, except now we're going to use students instead. So instead of just taking integers in our collection, we're going to take a more complex class of students. So if you remember from previous examples, my student class really has two key properties. It has the student's name and the student's GPA. And this code here in lines 11 through 16 just create my collection of Psych 101 students, and then it adds my 3 students to the collection. And then I have a print students method, which, as you know, will just go through each student and print out their name and GPA. And if you look, rather than using the for with a loop control variable, I'm using the for each construct of the for statement, which says in my collection of students, grab each student, name it S, and then print it. So I'm going to run this. But right now what I want you to know is it's going to take those students and print them out 3 times. What I want to do is I want to sort them first by name and then sort them second by GPA after I sort them by name. But if I run this right now, all it does is print out the students 3 times. It doesn't bother to go ahead and sort them either way. So Sally, Dave, Alice, Sally, Dave, Alice, Sally, Dave, Alice. What I want to do is take them, print them raw, then the second time print them sorted by name. So it would be Alice, Dave, Sally, then sort them by GPA in the last exercise. So as you can imagine, it's real easy to sort collections. You know that now. You just need to do this, collections.sort. You need to give it the collection you want to sort. I want to sort my Psych 101 students. And then you need to give it a comparator. And the same thing holds for if I want to sort them by GPA. But the difference is I'm going to give them a different comparator. So I don't know, I'm going to call this one. So what I have to do is I have to write these comparators. I have to say, what does it mean to sort by name and what does it mean to sort by GPA? And I will do that by writing my comparators now. So I'm going to call this one student name comparator. And again, every comparator needs to implement the comparator interface. So and this time I'm not comparing integers, I'm comparing student. And I have to override one method, the compare method. Student I'll use S1, student S2. Now what does it mean to compare these by name? Well, what are names? They're strings, right? So if I do s1 dot get name, that gets me the student's name as a string. So what can I do with that string? Let's find out. Oh, compare to. There we go. Ooh, that's even better. Compare to ignore case. Compares two strings lexicographically, ignoring case differences. This returns an integer whose sign is that of the calling compare to with normalized versions. Okay, so this is exactly what I want. So I want to compare s1 to s2 dot get name. If this is like, it feels like you have marbles in your mouth and you don't understand what's going on, how about if I wrote it this way? String student name, how about string name1 is s1 dot get name. This is probably easier to swallow for you. String name2 s2 dot get name. And then let's do the comparison. Name1 dot compare to ignore case name2. It's rather convenient that this method that I get automatically because I'm using a string, this method, when it compares name1 to name2, returns a positive value when name1's greater than name2, 0 when they're the same, and a negative value when they're less. It's exactly what I need for a comparator. That, by means, is no coincidence. That is by design. So now I have implemented my student name comparator, and I can go ahead and use it. Right here, I'm gonna sort by name using my student name comparator. So you define the class, but you need to use the object. So that's why I have new here. Let's comment out this line so it'll run. And let's execute it and see if it does sort them by name. So there they are, original, and there they are sorted by name. And it definitely worked. Sally, Dave, Alice, Alice, Dave, Sally. Excellent. Let's see if we can get them sorted by GPA now. In order to do that, I need to write another comparator that figures out how to sort them by GPA. And this is going to take some creative thinking. I'm going to call this student GPA comparator. Once again, this is going to implement comparator of students. I'm still comparing students, and I need to override my public int compare method of student s1 and student s2. These parameters could be anything I want. I'm just going to call them s1 and s2 though. I could go back to a and b if I really wanted to. Now I need to return something here. What I'm always returning is an integer. But what GPAs are doubles, right? So let's kind of use the same pattern we did before. Double GPA1 is s1 dot get GPA. Double GPA2 is s2 dot get GPA. Now you'd love to just say this, return GPA1 minus GPA2, but the problem with that is these are not integers, they're doubles. So before you think of doing something crazy like saying, well, let's just, cast that as an int. Think about what would happen if you did that. If I compare, suppose I compare a 3.7 to a 3.5. When I subtract them, I get 2/10, 0.2. And then I convert that to an int and it's 0, so then the comparison thinks they're equal. That does not help us out. So you might say, well, what if I convert this one to an int and then convert this one to an int and subtract them? Well, if you do that, you'll see it's the same problem. So what I have to do is I have to scale these out. And here's how that works. So we know that GPAs look like this, 3.972, right? So how do I scale this out to be an integer and still have it be accurate? Well, if I multiply that times 1,000, then I get 3972. That, as an integer, can compare to a different GPA like 3.971, which when you scale out to 1,000 ends up being 3971. And now you can see that GPA 1 is greater than GPA 2, and it's accurate. So that's going to be my trick. Told you we'd have to think about it. Most of the time when you're writing your own custom comparator, it's not as trivial as just comparing basic strings or basic integers. You have to do a little bit of thinking. So what I'm going to do is take my GPA and multiply it by 1,000 here. And then multiply this GPA times 1,000. And I want to cast those both as integers after I subtract them. So again, what this is saying is whatever your GPA is, multiply it by 1,000. So now there's no decimal points. Take this GPA, multiply 1,000. Now there's no decimal points. Subtract them. You'll get a double, but it'll have no decimal points. And then when I convert it to an int, I don't lose anything because there's nothing on after the decimal point anyway. If you want to be completely confident that this would be bug-free, you can always multiply it by a bigger factor. Rather than 1,000, you can multiply it by 10,000. But 1,000 works because our GPA goes out to 3 decimal points, right? So I'm pretty confident this comparator is going to work. The best way to find out if it's really going to work is to go ahead and use it and run it in my code. So here goes. Student GPA comparator. And let's see if that works. Basic, sorted by name, sorted by GPA, right? Now you might say, well, when I think of sorting it by GPA, I want the bigger GPAs at the top. I don't want the smaller GPAs first. I want the highest GPAs first. That's kind of what I would think of as sorted by GPA. So we can fix that really easily. Hopefully you figured this out by now by just negating this. So if I take that and put a minus sign right there, that does exactly what we want. Now they're sorted with the highest GPAs first. I encourage you as you go through this lesson to debug this code, step through it a line at a time, really see what's happening here. Throw a breakpoint down here under student comparator, student name comparator, student GPA comparator, and watch what's happening as the arbitrary values of S1 and S2 trickle in from my collection. Well, that concludes our lesson on sorting and searching. I hope you learned a lot about how the process works. Thank you so much for watching, and I welcome your questions, comments, and feedback on YouTube. We'll see you again real soon. Thank you. Bye-bye.